Systems of equations. Many problems require two or more equations to be satisfied at once in two or more variables. A solution to a system is an ordered pair that satisfies each equation in that system. If we find the set of all solutions, it is called solving the system. There's several ways to solve these systems. Method one is substitution. It has 5 steps. We're going to pick one of the equations and solve them. Substitute that answer into one of the other equations, solve the equation we just generated from step 2, do what's called back substitution, and then check our answer. So we're going to try the following example. We want to find something that satisfies both 2x plus y equals 5 and 3x minus 2y equals 4. To help us out, I'm going to number these two equations. The top one I'll call equation 1, and the bottom one I'll call equation 2. Step 1 says solve one of these. I'm going to solve equation 1. There doesn't seem to be an advantage to either of them in this case. And I'm going to solve it for y. I take 2x away from both sides. And I get y equals 5 minus 2x. Note, it doesn't matter which equation I solve or for what variable I solve for. The important thing is that next I want to substitute that new information I got from equation 1 into equation 2. Think of it as using up your clues. We're trying to solve this puzzle. I just used clue 1. Now I need to use clue 2. We do not want to substitute the answer we just got back into itself. That won't get us anywhere. What I just learned was that y is equal to 5 minus 2x. So in equation 2, I'm going to replace that y with 5 minus 2x. Solve for x. I now know that x equal 2 will satisfy both equation 1 and equation 2. I need to find the corresponding y value. So now we do what's called back substitution. I now need to take the x equal 2 fact that I generated from equation 2 and place it back into equation 1. This is the back substitution step. So in equation 1, I substitute x for 2, solve, and I get y equals 1. So I believe the solution to this equation is y equals 1, x equal 2. I can now check this. I plug this point. It needs to satisfy both equations. Sure enough, 2 times 2 plus 1 is 5. 3 times 2 minus 2 times 1 is 4, just as I wanted it to be. So the point 2, 1 is on both equation 1 and equation 2. So these are the steps we would need to do the substitution method. We're going to change pace here for just a second. What is a graph? No, really, think about what a graph actually is. The graph is a visual representation of solutions to the equation. Any location on the line is a point that is a solution. So let's go back to our example here, and let's graph. I'm going to graph equation 1 in green and equation 2 in orange. Anywhere you put your pen, your finger, whatever it is, anywhere on that green line would be a coordinate, an xy pair, that would satisfy 2x plus y equals 5. Same logic for anywhere on that orange line. So if I want a point that satisfies both of those equations, it needs to be a point that is on both lines. Where does that occur? Right here, at 2, 1. This is our second method. It's the graphical method. The solutions of a system correspond to the points of intersection of the graphs. So if I have multiple lines, it needs to be a point of intersection of all of them. We have one more method to talk about. Method 3, elimination. Let's look at a new example. 2x minus 4y equals -7, and 5x plus y equals -1. The goal here is to take multiples of one of these equations, or both, to get something to cancel. Let's zoom in, let's pay attention right here to -4y on the first equation and plus y on the second equation. I'm going to multiply that second equation by 4. You'll now note that in the top equation, equation 1, I have -4y, and in the bottom I have a positive 4y. I'm going to take and add equation 1 to equation 2. Because I multiplied by the 4, I get cancellation of the y's. So when I add these two equations, the left-hand sides and the right-hand sides, all I get is 22x equals -11, no y. Solve for x, get x equals -1/2. I back substitute. I'm going to take that x equal -1/2 and plug it into the first equation there. I get y equals 3/2. I'm ready to check my answer. As I got y equals 3/2 from the first equation, I'm not going to plug in my supposed solution, x equals -1/2, y equals 3/2 into equation 1. I'm just going to check it in equation 2. I have the equal sign with a question mark there because I'm asking, is the left-hand side equal to the right-hand side? At the bottom there, at the end of my work, I'm asking, is -1 equal to -1? Yes, it is. So these are our 3 methods for solving systems of equations. A few comments. Let's run through some scenarios with method 2, the graphical method, because it's just going to be the fastest to view some of these. Here I have a system. The equation 1 there can be quickly rearranged. You can see that's just a linear equation. It's a line. Equation 2, on the other hand, we know from our parent functions, that's a cubic. So if I graph them real quick, there's my line being graphed. Here's my cubic being graphed. It's not exact. It's a rough sketch, but we can see what happens here, that I have 3 points of intersection. So a system can have multiple solutions. What's this going to look like if we can use one of the other methods? Well, the method of substitution, we can see that we get 3 potential x values. Once you use back substitution, you will get the 3 corresponding y values. Let's look at another scenario. Here, equation 1 and equation 2 are both just linear equations. So let me graph x plus 2y equal 5. It's that black line right there. And now let me graph the second one. Looking closely, I can see that equation 2 is just double equation 1. The 2 lines are exactly the same. This would lead to a case where a system can have infinitely many solutions. What does this look like? Well, when I use the elimination method, I can see that I get a statement like 0 equals 0. This is always true no matter what I choose for x or y. One more case to look at. We already know what the graph of x plus 2y equals 5 looks like. Now let's go ahead and graph 2x plus 4y equals -2. They're parallel lines. They have no points of intersection. A system can have no solutions. Again, let's see what this looks like with the elimination method. I get a statement like 0 equals 6. As that is never true, this system has no solutions. I want to give a preview of where the course is going to end up. Here I have a system of 3 equations and 3 variables, and we're kind of going to get tired of writing these. They're going to get really long and we're just doing the same thing over and over and over. So what we're going to start to use is an organizational setup to just eliminate some of the busy work here. The first thing that we do is we vertically align based on the variable. Importantly, you'll notice equation 3 there does not have a y term, but I still need to account for it. So it's just a blank space right now. Next, I'm going to clean this up a little bit. Those plus signs are distracting, and I need to go ahead and reveal the invisible ones that we don't usually take the time to write out. Note, I place a 0y in equation 3 to indicate that placeholder. Next, the time saver comes in that we are not going to write the x's, the y's, the z's, and the equal signs. It's just understood that everything in that first column is the coefficient of an x. Everything in the second column is a coefficient of a y, and so on. To indicate that we're using this sort of organizational scheme, we put it in large brackets. This is called an augmented matrix. One other comment, the dimension of a matrix is m by n, where m is the number of rows and n is the number of columns. In this example, as we have 4 columns and 3 rows, we have a matrix that has dimension 3 by 4.